Hello everyone, this is Surya Prakash and then my groupmate Danish Raja. So it's our proposed project is like this project integrates about the object detection, depth estimation and the orientation prediction into the unified 3D perception pipeline. So the first slide, what's the main goal of our project is like the goal is accurately determine the object depth and orientation to maintain the yarn pitch and roll of the multiple object in real time using the single RGB or and webcam. This is direct application in robotics, augmented reality, autonomous navigation, and spatial understanding. So so I can explain about the three things of the object detection and the estimation and the orientation estimation. So first I tell you about the object detection in the ULO V8 in the deep learning based real-time object detector that identifies the classified object with using the bounding boxes optimized for speed and accuracy. So the depth estimation with MIDAS. So it's like a monocular depth estimation model that predicts the absolute distance of each object or scene element for the camera using the single RGB image, and then the orientation estimation with the efficient net. This model using the efficient net to regress the 3D orientation of detected object by estimating their yawn and pitch and the roll angles from the visual features. Okay, now the proposed methodology. So we use the three models. So the first model is like the object detection using the EOLO V8. It's like fully trained with specific data sets. And the second one is the depth estimation using the MIDAS. It's like fine tuned. And then orientation estimation using the efficient net. It's like trained from scratch. So now about the data set. So we use the Kitty data set because like it's provide the stereo images, volatile the LiDAR point clouds, calibration files, and the depth maps for supervised learning. And then the validation sections crop, it's a directory, so used for the fine tuning with the Valentine for the generation of 3D orientation labels. And also the data pre-processing involves the resizing, clipping, and normalization for both image and the depth input streams. So it's now about the models. So it's about the three models, the YOLO V8. So we use for its lightweight object detection model. So used to detect objects in the frame with the bounding boxes on the classes label. Second one is MIDAS. It's like the transformers based model used for monocular depth estimation, fine tuned for the Kitty dataset. And the third one is efficient net used for prediction orientation angles, yawn, pitch, roll of detected object crops using the geometric supervision. Tools and library which we just used for the ULO 8 for high-speed object detection, Hugging Face transformers for the MIDAS model loading and fine-tuning. Open3D is for to process the Valentine point, the clouds and the extract orientation using PCA. PyTorch and Torch Vision for training efficient net and the running inference. Matplot for the to visualize the loss curves of RMASI on the MAE for the training loss.
So I am Dharnesh. I am going to continue the presentation. So the object detection training. So here is the training what we had done for object detection. So we used YOLO V8 nano version. So it is trained especially on a BDD 100K dataset. So the input resolution of image is 640 into 640 and the epochs are 100, and we trained on a batch size 16, and the optimizer I have used is Adam optimizer. So I have split the dataset into two different categories. For the train, I took 80% of as a train dataset, and for 20% for validation. So I for the loss function I got object loss, class loss, and bounding box loss. So IOU based bounding box regression loss. So what are the augmentation techniques I have used for data is mosaic tiling, random cropping, horizontal flipping, and brightness contrast variation. So these are the four kind of data augmentation techniques I have used for the object detection. So for training a depth estimation, actually it's a transformer based model. So it's a already trained model. So I just fine tune the model with a specific data set. So the model I have, how I pulled was like Midas with DPT large transformer backbone, and the data set how what I have used is Kitty with lidar based ground truth. So the for fine tuning a Midas model, the data set RGB image size is 384 x 384. So this also trained for 100 epochs, and the batch size is 2. So what is the issue I have caused while training is like the batch size is, while I kept 4, the training has stopped, so I changed the batch size into 2. So optimizer is same Adam W, and the learning rate is like 1 into 10 power minus 5. Same, the dataset split has been done in this fine-tuned model. So for inference details, full frame depth maps predicted, metrically scaled, used Kitar LiDAR supervision. The inference speed is 43.5 ms per frame on RTX 4060. So post processing applied, percentile clipping and guided filtering. Why we use guided filtering? Because the depth estimation model gives a relative depth, not absolute depth. For boundary refinement, we use guided filtering. So here is the same what I have done so far. So automated orientation labeling using Velodyne and PCA. Why it is needed is manual annotation of yaw and pitch is expensive, and I mean like we cannot annotate each data using manual labeling. So use Kitty's Velodyne point cloud, project points into 2D using calibration matrices, apply PCA to object clusters. So output is like extract first principal component, gives direction vector, compute yaw and pitch. So benefits is fully automated labeling, accurate real world orientation without human effort. So this is the this is the architecture that how I generated a label for orientation estimation. So first identify objects in images using YOLO V8, project lidar point onto the image plane. So then isolating points within bounding boxes and estimating object orientation using PCA, and at last it compute the yaw and pitch angles. So this is the steps that I have explained so far. And what is point cloud is? A point cloud is a collection of individual data points in a 3D space. So each point represents a precise location in the real world. So LiDAR stands for light detection and ranging. So it is remote sensing method that uses laser beams to measure distances. So this is the training loss curves that I have done for orientation estimation. So it consistently decreases. The model is learning orientation well. So initially high end drops significantly, meaning that model is learning rotation around the vertical axis. So it is the best one. So more stable, lowered compared to yaw, suggesting moderate difficulty. So why we tell us a unified real-time inference is like webcam input is passed through YOLO V8 for detection and Midas for depth and EfficientNet for orientation estimation. So depth predictions are normalized and clipped for better scaling. Orientation is computed for each object crop using a trained regression model. So all predictions are visualized on the screen, real-time annotations of labels, confidence, depth, yaw, and pitch and roll. So this is the final architecture that I have designed. This architecture is our own architecture what we have done in this project. So these are the real-time results. So here is like first I have worked for the detection and depth. So it's the result for detection and depth. So first it detects the person, bicycle, car, and traffic lights, so on. So the 0.2 meters is like the from camera to the object. So these are the real-time results that I have tested in my lab. So these are the results from taken from a webcam. From these are the real-time results which shows the relative depth. So here is the breakdown of one image. So the teddy bear, so it detects the object as a teddy bear, and confidence score is 0.87, which is high confidence, and the estimated depth is like 1.9 meters. So how far the object is from the camera and the matrix. So orientation is nothing but yeah is like the object is slightly turned to the right, and pitch is like the object is pitched slightly downward. So these are the result images of our project. So these are the comparison with previous work. In the comparison, you can find our model is learning good and fine compared to other models. So we achieved a better accuracy in this. So that's it for the presentation. Thank you.